Okay, so this is our second video on functions, and we're going to start off here looking at a new class of functions that some of you might have seen before. These are called piecewise defined functions. And basically, piecewise defined functions just means that there's more than one equation to define the function. And I think the easiest way to kind of go through them is just to look at the functions as an example and then just go through that. So the example we're going to look at here is f at x is equal. Now the way that piecewise functions are defined is you write a set of curly braces and then you put each piece down, x squared plus 1, and then there's got to be some condition here. And the condition we have for this is if x is less than 0. And then we have another piece, and that piece is x minus 1 if x is greater than or equal to 0. Now we're going to go ahead and do some evaluations here, and then we'll graph it as well to see how you would graph these. Find f at -2, f at 3, and then f at 0. So we're just going to evaluate them. Now this is not really that much different than what we did at the end of the previous video. The only difference here is that we have to pick the correct piece here. So if I'm doing -2, I'm substituting x equals -2 into the function. Well, which does that satisfy? Is -2 bigger than or equal to 0, or is -2 less than 0? And pretty quickly we can clearly see that -2 is of course less than 0. So that means I'd want to use this top equation here. So this would be then that it's -2 squared plus 1, which of course is just 4 plus 1, which is 5. Now let's go ahead and look at f at 3. So again, the first thing you want to do is identify what piece should be using. Well, x is 3, and so we have to determine which one of these inequalities is true. And clearly 3 is bigger than or equal to 0, so that means we would be using the second equation here. So f at 3 would simply be 3 minus 1, which is 2. And then the last one is the exact same thing here. The reason I included this one here is it's at 0, and so that's, you have to make sure you pick the correct one, and of course you're looking for the portion that is also allowing x to be equal to 0. And clearly we can see on the second piece here we have it is being greater than or equal to 0, so I'd be using the second piece again, and so this would be 0 minus 1, which is equal to -1. Now, what I like to do if we're talking about graphing these is, I'll bring up a graph here, is first plot the points at the transition point. What do I mean by the transition point? I'm talking about, in this case we have one transition and it's at x equals 0. So let me write the function down again here so I don't have to keep scrolling back up and down. So f at x is equal to x squared plus 1 if x is less than 0, and it's equal to x minus 1 if x is greater than or equal to 0. So I like to plot both of these here. Now what I'm going to do is we're actually going to evaluate both of these things at 0. 0 squared plus 1, which is equal to 1, and then 0 minus 1, which you already did, which is equal to -1. So this of course was for my top piece, and this was for the bottom piece. Now I'm evaluating at x equals 0. Now the bottom piece is the one that actually is allowed to be 0. So that means -1. I'm actually going to have a point at 0, -1. So I'm going to put a solid dot there. Now the top one, I'm not allowed to actually be 0 in the top one. However, it's x less than 0, so I can go all the way up to 0. And if I was allowed to have 0, the value would be 1, but since I'm not allowed to, what we do is we put an open circle right there. So I put an open circle at 1. And then we're going to look at graphing each of these pieces individually. So if we look at x squared plus 1, I'm not going to write down the computations here, but we could see here, if we did this, f at negative 1, I'm going to plot some points here. This would be equal to 2. So we'd have this point right here. And then if you did f at negative 2, this would be equal to 5. So 3, 4. And of course we know this is a parabola shape, and so this is going to go up like that. And then x minus 1, well, that's actually just got a y-intercept of negative 1, which we already have plotted, and the slope here is just 1. So the slope would be going up 1 and over 1, up 1 and over 1, so on and so on, and then we would draw our straight line. And so this would be the graph of my piecewise function. Now I want to emphasize that this still does pass the vertical line test. Some people, if you draw a vertical line on the y-axis here, they're like, you're hitting 2 points. I'm not hitting 2 points because the open circle is not saying there's a point there. It's saying I go all the way up, but there's actually no point there. But the closed circle is a point. So I still actually only hit 1 point on the y-axis there with a vertical line. Alright, so piecewise functions are used. I mean, they're just an interesting kind of function. I wouldn't say, oh, we use them all the time, but it's definitely important to understand them. Alright, the next couple examples that I'm going to do one example of a couple concepts here that quite frankly aren't, again, new. That's just terminology is different. So, finding when f at x equals 0. Now, as I said, this is actually something we've done before. If you want to think about this in terms of a graph, all this is doing is finding x-intercepts. So let's just look at a quick example here. If we have f at x equals x squared minus 16, and then we're wanting to know when find when f at x is equal to 0. So, well, f at x is 0, so I just say, well, I want to know when 0 is equal to x squared minus 16. And now we have to apply all of the solving techniques we've talked about in previous videos. So this would be factoring, of course. 0 would factor, this would factor to x minus 4 times x plus 4, which gets me the answers of x equals 4 or negative 4. So not really anything complicated here. The only thing that can be challenging about these problems is just the level of difficulty of the equation. But this is all stuff we've done in previous videos. So you just set the function equal to 0 and you solve for x. Alright. Finding when f at x equals g at x. Now again, this is something we really have done before, and once we see it, you'll see this is just solving equations again. So let's look at an example here. So we have f at x is equal to x squared plus 6x minus 24. G at x is equal to 4x minus x squared, and we want to find when these are equal. So if we want to find when these are equal, well, what do you think we're going to do? We're going to set the equations equal to each other. So I want to know when is x squared plus 6x minus 24 equal 4x minus x squared. Now, as I said, this is really something we've done before, because this is just solving a quadratic equation where we have to move everything to one side. Now, as far as interpretation of this on the graph, what we're actually finding is we're finding where the graphs of f at x and g at x intersect. Alright, so then let's go ahead and finish this problem out. So we'll move everything to one side. So we'll add the x squared to both sides, so you'd wind up with 2x squared. I'll go ahead and take it in a couple steps here. Plus 6x minus 24 equals 4x. Subtract the 4x from both sides, and you would wind up with 2x squared plus 2x minus 24 equals 0. Now sometimes people at this point want to just pull out the quadratic formula, but I see right away that I could at least factor out a 2, and if I factor out a 2, maybe the problem won't be too bad to factor. So you get 2 times x squared plus x minus 12 equals 0. And then if I look at this for a second, I can see, yeah, this does factor, and this would factor to 2 times x plus 4 times x minus 3. And then this is equal to 0, and so we would get then two answers, x equals negative 4 or 3. Alright, and so that's where f at x would equal g at x, at those two values here. So, as I said, I could do more examples of those, but that's really something we've already done before. What I'd really like to wrap up this video with and spend some time talking about is finding the domain of functions. Now, remember the domain was that set X, but really we want to think about domain that is the allowable inputs. Remember how we said we had the function box and we had the X values were the inputs and then the outputs were those Y values. The domain is the allowable inputs. So let's find the domain of the following functions. Well, let's start with what I would consider, sometimes people find this to be a hard example, but I think it's an easy example. F at x equals 3x squared minus 4x plus 5. And to find the domain of functions, all you're saying is you want to say, hey, is there an x value that I could substitute in that doesn't work, meaning that I couldn't compute a number? Because then that would mean that it wouldn't be in the domain. Or you can think about it as like, what x values can I plug in and actually be able to compute something? So let's look at this quadratic equation here. 3x squared minus 4x plus 5. Could I plug in any value for x and compute it? Well, we should convince ourselves pretty quickly that, yeah, I can put in any value for x and compute it. I can square any number. I can multiply any number by 3. I can multiply any number by negative 4, and of course I can add or subtract any numbers that I want to. So there's no restriction on the numbers here for the inputs. So the domain here is all real numbers, which occasionally you'll see me, or books will sometimes use this, as an abbreviation for all real numbers. You'll see a capital R with 2 lines. It's actually a font called Blackboard Bold, and sometimes we do use that as a shorthand for all real numbers. And I'm okay if you use that as a shorthand for all real numbers. But I'll write it out often. Sometimes I'll use the R, so you should just be aware of that. Alright, so let's look at another one here. G at x is equal to the square root of x plus 5. Alright, now I do have to think about this, and again, not that this is going to be hard, but I have to think about square roots. What do I have to be careful with square roots? Well, we talked about this in an earlier video. If I do square roots of negative numbers, well, I can do those, but I get imaginary numbers or complex numbers. And remember, at this point in time, we're only concerning ourselves with real valued answers. We only want real numbers as my answer. So in order to get a real number, we have to make sure what's inside this square root is bigger than or equal to 0. In other words, we have to have x plus 5 being greater than or equal to 0. Now you can kind of see why we spent some time solving inequalities. As I've mentioned in other videos, math kind of builds on itself. Well, we had to talk about solving inequalities. This is one reason, not the only, one reason we needed to solve inequalities. This one is an easy one to solve, of course. So you just get x subtracting 5 from both sides has to be greater than or equal to negative 5. So the domain is all real numbers. You might say, wait, it's not all real numbers. I'm not done writing this. All real numbers such that x is greater than or equal to negative 5. Now, that's one way to do it. Another way to write a domain down, why can't I erase this? Another way to write a domain down is to use interval notation. And if we used interval notation, we'd have square bracket negative 5 to infinity. And a lot of people prefer writing the interval notation. As a side note, let me move back up to this previous problem. If you want to do interval notation for all real numbers, it's just going from negative infinity to infinity. That's how you could do interval. So either you can use interval notation like this, or you do have to write something like all real numbers such that x is greater than negative 5, greater than or equal to. Alright, let's look at one more example of finding a domain here. So let's look at h at x equals 1 over x squared minus 4. Now, we have an x in the denominator here. And we have to be concerned about that because whenever you have a variable in the denominator, we have to be concerned about getting a 0 in the denominator. We've already mentioned a couple times you can't divide by 0, so I have to be aware of that. And so really what I need to know is when is x squared minus 4 equal to 0? Because if I know when it's equal to 0, those are going to be the points that are invalid, because I can't divide by 0. But any other number, no matter how big or small that number is, I can divide by. You know, I can divide by 0.00000 going on a long time, 1, for instance. I mean, I can divide by any number, or I could divide by, 1 billion. You can divide by any number as long as it's not 0. Alright, but again, this is easy to solve. I have x squared minus 4, so this is just x minus 2 times x plus 2 equals 0. So I get x is 2 or negative 2. That's what makes my denominator 0. So the domain then, we would write, is it's all real numbers. And actually, I'll say all real numbers x to be a little bit more proper, such that x, not such that, all real numbers x, I mean I could write it, I think there's just a better way to write it. All real numbers x except x equals 2 and x equals negative 2. So all real numbers x except x being 2 and negative 2. Now you could write this in interval notation as well. Interval notation isn't quite as nice, I think. This would be negative infinity to negative 2 unioned with negative 2 to 2 unioned with 2 to infinity. Now you really should be comfortable though writing it either in words like this or writing it as the interval. It's good to be comfortable with both. Alright, so we're going to move on to another topic here, but as I say in the next video, we're still going to be talking about functions, and pretty much we'll be talking about functions in some form probably for the rest of the semester.